Welcome, ladies and gentlemen. This is our second video on kinetics. The goals of this video will be about learning something called the integrated rate law. And for this video, we're going to be focusing on what is the integrated rate law for first order reactions only. We're going to look at integrated rate law with different orders in the next video. So this is going to be about looking at different sets of information than we were looking at in the first video. In this one, we're going to be looking at information about concentration and time to figure out new concentrations or to figure out time. So it's essentially a different way of dealing with order and looking at order. It's concentration and time rather than different trials with different concentrations and different rates. So, integrated rate law, first order reactions. Well, let's step back and just think about first order reactions for a second. What is true about first order reactions? Well, first order reactions only depend on the concentration of a single reactant. We've seen that definition time and time again, that it depends directly on a first order reaction depends directly on the concentration of one reactant. So things that we know are true about a first order reaction. Well, we know that rate is equal to the change in concentration of A over the change in concentration of, over the change in time, right? This is our definition of rate right here, right? Delta A over delta T. We saw that on day 1 of kinetics in your POGL. So we know that if that's the definition of rate, right, how concentration changes over time, that must be true for all reactions, including first order reactions. We also know that for a first order reaction, rate is equal to K times the concentration of A raised to the first power. That's the rate law. That's the rate law that we've seen, again, since day 2 in our kinetics unit. Well, if they're both equal to rate, change in concentration over change in time, and rate is equal to K times the concentration of A raised to the first, then they must be equal to one another, right? They have to be. That's mathematically a true statement. Well, if we set them equal to one another, and now we have change in concentration of A over change in time equals K times the concentration of A, and we use magic calculus. Basically, we're integrating with respect to A and time, so concentration of A and time. Then we get this equation. Now, you don't have to understand how we get this equation from the first statement, but you do have to understand that we do get, in fact, get this relationship, that the natural log of the concentration of A at time t minus the natural log of the concentration of A at time 0 is equal to minus KT. So this is actually a really important statement right here, and this is what we call the integrated rate law. So it's sort of like what happens when you take the definition of rate, set it equal to the rate law, integrate it, use some magical calculus, and we get this statement where, again, AT, concentration of A at point T, A0 is our initial concentration of A, and T is time. Now this one right here, which is on your reference table, I'm going to be pointing that out, that is on your reference table in the kinetics section. If you rearrange that equation just a tiny little bit, if you basically just add the natural log of the concentration of A at time 0 to both sides so that you're bringing this over to the right-hand side, we get this. Right? All I did is I moved it to one side. That's it. The reason I did that, though, very, very, very important reason, because this fits a pattern. This, how we've rearranged it, fits a mathematical pattern that I hope you would recognize. And in class, I'd give you a little bit of time to think about it, but this is a video, so I'm going to cut straight to the chase. This is y equals mx plus b, right? This whole thing is y, k is m, t is x, and natural log of A at time 0 is b. What's critical about that is y equals mx plus b is slope-intercept. It is a straight line. And that is really the huge point about this. It means that there is a graphical relationship between concentration and time, but for first order reactions, that in that relationship, you will only get a straight line if you are graphing time versus the natural log of concentration of A. So graphs are so important in kinetics, and this next sort of portion of kinetics, we'll be looking at when does what order get you a straight line. For first order relationships, based on the calculus that's involved, we get a straight line when we graph natural log of concentration of A at time t versus time. So big point. Now, when you're graphing this, again, looking at what's slope, K is slope. So this is actually a way to get the rate constant. Graph it, you get a straight line, take the slope, and it's actually just going to be the absolute value. So K is always going to be positive, so slope is equal to negative K. And your y-intercept is natural log of A at time 0. Things that are true of first order reactions. All of these statements are true about first order reactions. We have rate is equal to change in concentration of A over change in T, right? That's our definition of rate. We have rate is equal to K times concentration of A. This is our rate law. And now we have our integrated rate law. These are all statements that are true about first order reactions. And looking at the graphs, we have different axes. We have concentration versus time. In the first one, we have natural log of concentration versus time, and we have 1 over concentration versus time. And for first order reactions, for concentration of A versus time, we get a curve. For 1 over A versus time, we also get a curve. But for the natural log of concentration versus time, we get a straight line. And that is our focus, because this is actually going to be a way that we can determine order. If you graph concentration of A versus time and you get a straight line, that tells you that your reaction is first order, if nothing else in the problem was indicating that to you. So looking at a problem, a very typical problem that can be asked about this type of question, the kinetics question, we have this one. The reaction 2A goes to B has a rate constant of 2.8 times 10 to the negative seconds to the negative first at 800 degrees Celsius. How long will it take for A to decrease from 0.88 molar to 0.14 molar? First of all, notice that there's sort of a different set of information that's been supplied to you in this problem than it's been supplied to you in the previous questions that we're looking at with the first video. Now we have two different concentrations. We only have one trial, right? That they did not run multiple trials, they ran one trial, and it's asking about time, right? How long? It's asking you to figure out a time, and we have a starting amount, right? We have, this is sort of A at time 0, and we have a final amount, A at time t. Make sure you're reading that carefully, right? A at time t is not going to be your larger value. It's actually going to be your smaller value. And it's giving us the rate constant. Now, we have this equation from our reference table, natural log of A at time t minus natural log of A at time 0 is equal to minus kt. But this is true for first order. And nothing in the problem, I mean, I know the title says it, but nothing in the question blatantly says this is first order with respect to A. So how can we sort of prove that, yes, we are allowed to use this first order integrated rate law for this problem? Where is the problem telling us that it's first order if it's not blatantly coming out and telling us that it's first order? Well, it does actually tell you somewhere. I wouldn't give you this problem unless somewhere it indicated that it was a first order reaction. And if you're really on your game, you know that's where it tells you first order. Remember, the units on K tell you order. The units on K are a direct comment about the order of the reaction. They cancel out all molarities except for one and provide the per second component. So if there is no molarity at all anywhere in your K value, that means that there was only one molarity in the rate law, meaning that K didn't want to cancel it out all molarities except for one. So these are the units for a first order reaction. So we know that it's first order. By giving us K, by giving us the units for K, they have told us the order of the equation. And then it's simply plugging in and solving. That's really all this question is. It asks for time, it gives you initial and final concentrations. Bam, that's integrated rate law. That's that equation that's on your reference table. So we're simply plugging in. So natural log of concentration of A at time t, that's 0.14 molar. Minus the natural log of the concentration of A at time 0, that's 0.88 molar. Careful when you plug in, right? It's not always, large number minus small number. You have to think about this and plug it in correctly. Is equal to minus k, so that's minus 2.8 times 10 to the negative second, seconds to the negative first, times t. It's just solving. That's all it is. That's all it is. So going through, I sort of combine some steps. I get negative 1.838 is equal to minus 2.8 times 10 to the negative second, seconds to the negative first, times t. And I get a t value, and I get 66. And then thinking about what unit it's going to be, I know that the time unit here is going to be seconds because of the unit on k, because k is in seconds. If k had been minutes to the negative first, or hours to the negative first, or even days to the negative first, then I know that that would have been the unit for t. So I'm looking at the unit on k to get me the unit for t. And that's it. That's all we're doing in this problem. Integrated rate law, concentration and time, change in concentration with respect to time. So it's a different set of information, so we're using a different method to solve. We can't use the method of initial rates here. We don't have initial rate. We have nothing here is directly giving us rate, so we need to use the integrated rate law. Now, first order reactions, half-life. Half-life actually pops up again here because half-life, which I know you think of as a nuclear chemistry thing, is actually not exclusively about nuclear chemistry. Half-life by definition is simply the time required for the concentration of a reactant to decrease by half, or for, half of a radioisotope to decay. But think about that. That's kinetics. How long does it take to get to half of what you started with? That's kinetics. How long does it take? How long does it take? That is chemical kinetics right there. Half-life is actually kinetics. We don't teach it in the right unit in Regents chemistry. What a shock. Now, for first order reactions, using our integrated rate law, I'm going to prove to you how we can get half-life out of this equation, and how it actually only involves a tiny bit of math, how ultimately at the end it doesn't really involve that much of a calculation. So this is our integrated rate law, and if we're looking at this in terms of half-life, as I've noted right here with T1 half, then that means that I actually know what AT and A0 are, even if I don't have the actual numbers, because the definition of half-life says it's the time required for the concentration to decrease by half, meaning I know that the natural log of the concentration of A at time 0 is always 0.5x, meaning 0.5 of whatever it initially was, and the natural log of A at concentration of time t is 1x. Half-life is always half. It's always half. Half of whatever you started with. Maybe you started with 0.12 molar. Then the amount you have left after one half-life is 0.06. Maybe you started at 20 molar. That means that the amount you have left after one half-life is 10. Oh, it's always half. I don't need to know what x is. I just need to know that it's half-life and that it's gone down by half. That's it. That's all I need to know. So x is actually irrelevant. It's the half-life bit that is all I need. Now, using natural log rules, I can actually combine this portion right here, and I can make this be the natural log of 0.5x over 1x. So this is just this is just math. This is not chemistry at this point. This is just saying, okay, if I'm subtracting two natural logs, I can actually combine them by dividing them. Is equal to negative kt 1/2. Oh, and look, x is canceled out. X has gone away. The x is irrelevant. It's the half bit that's important. And now I'm stuck with the natural log of 0.5. That's not a variable. That's a discrete number, right? So I know that I'm just on my calculator plugging in the natural log of 0.5. I get negative 0.693 is equal to minus kt 1/2. If I simply bring the k over, divide both sides by negative k, right, negative k, then I get this equation right here. T1/2 is equal to 0.693 over k, which, if you look at your reference table, is actually on there. So this is our half-life for first order reactions. And it just comes straight from our integrated rate law, and that's all it is. T1 half equals 0.693 over K. It's simply taking that integrated rate law for first order reactions, plugging in half of your concentration, and going from there, and you get that equation. So half-life, just one thing that I want to point out about it, half-life, if you remember from Regents, you're only losing half each time, meaning you don't start at 100, then go to 50, then go to 0. That's not what it is. You start with everything. So this is our first half-life. If you count up the dots, we have 16 that are in here. And then you have your second half-life. So we go to 8. So okay, we went down by half, but then you keep on taking half, meaning you're never actually going to get all the way to 0. And this is our third half-life. And now we have 4, right? So we took half to get to 8, then we were taking half of that to get to 4, and then this is our fourth half-life. So, and we have 2. So again, we're taking half to get to 2. So you never, again, with just this is a recall, hopefully, with half-life, you're constantly taking half of whatever you have left. So just a half-life problem. What is the half-life of N2O5 if it decomposes with the rate constant of 5.7 times 10 to the negative 4th seconds to the negative 1st? Again, we have the equation that's on our reference table. T1 half is equal to 0.693 over K, but this is only true for first order reactions. It's different for second order. So how do we know that we're allowed to use this for this particular problem? How do we know that this problem is telling us that it's a first order reaction? Hopefully you feel comfortable. Boom, there it is. First order units for K. So we can simply plug in T1 half is equal to 0.693 over 5.7 times 10 to the negative 4th seconds to the negative 1st. And if you think about that unit for second, by putting sort of per second in the denominator of a fraction, you're actually going to bring that second unit up to the numerator, and then you're just mathing it out, right? T1 half, when I solve this, I get 1216, but taking into account significant figures, we only have 2 in this. I'm going to round that to 1200 seconds. I didn't ask for a unit on T, so I'm going to leave it as seconds, but you certainly could put it in minutes if you really wanted to do an extra calculation on that problem. And that's it. That's integrated rate law for first order reactions. So you'll be doing some problems with that tomorrow.